Was that one the most recent one?
3 and 4, yes. Now, I don't owe you any quizzes anymore. So I graded all the quizzes, and you have all the homework. So only one thing is left is midterm. So this is quiz 4, quiz 3, and also homework 3 for you to grade. Anybody doesn't know about the grading rules?
Well, when do you want them back?
When?
Yeah.
Anytime before the final.
Okay.
Just to give you a grade.
Okay. So I need
And the rule is if you skipped a mistake, then this will be 0 for the whole homework, right? Whenever you find a mistake, you have to take off the least amount of points, which is half one mistake out there, right?
Do you just want the grade or do you want?
No, I want the whole thing. So if you want to take a picture for it or something, take it for your final. Okay, so this is homework 3. I posted the solution if you didn't notice. Quiz 3 and 4. There was a question here about quiz 4. So when I give a quiz, this is really to help your grades. So it becomes a little bit pretty sad for me when it doesn't help. There are going to be no more quizzes, just to be. So the rule was, and I told you this from the beginning, but probably you just passed it, didn't pay attention too much to this grade. The quiz is intended to be really simple. So last time I gave the quiz, I mean, many people did well, but not many. Let's say some people did well. So I give this J is integral of x dot squared over t cubed dt, and I want to minimize that x0, 0, x2 is 16. One thing that I was really sad about is that people dealt with this as a constraint, and I don't know how they try to formulate a constraint and formulated an augmented Lagrangian. This is pretty complicated. Of course, I will not give it in a quiz. This is the simplest problem calculus operation. Remember that we got 3 problems. Simplest problem, constraint with integral constraint, we call that isoperimetric, and finite constraint. This is the first one. Just minimize J. Please, I have here 0, 0, x2, 16. These 2 points, I want to connect them, and I don't know how. How to connect them and minimize this J. This is pretty straightforward. You have your F, and you know the equation. D by dt, partial F, partial x dot, minus partial F, partial x is 0, that you are expert on. I mean, if you got a mistake while evaluating these partial derivatives, it really sucks here, but I mean, few people did that. Obviously, F doesn't depend on x. Partial F, partial x, that's simply 2x dot over t cubed. And here is where people divide it. Now, so far, almost so good for everybody, except for the few who dealt with this as a constraint and who formulated an augmented Lagrangian, but that's fine. Please, if you say d by dt for something is 0, this means that it's constant. T x dot divided by t cubed is simply some constant c, c1, c2, whatever. Don't go and differentiate and get a second order differential equation with time varying coefficients, and you have a mess. You can do that, try to solve, and probably you'll get 8 out of 10, that's fine. But this is very simple. Now, x dot is c1 t cubed over 2, so x of t is very simple, right? c1 t4 over 8 plus c2, and you have the boundary conditions to get c1 and c2. In particular, x is 0, 0 gives you c2 of 0. And x2 is 16, you can know now that c1 is 8 or whatever, and the solution is x of t is t plus 4. So pretty straightforward. I cannot get more simpler than this in a pop-up quiz. Otherwise, I'll be really harsh. I mean, if you really want to give a pop-up quiz that is reasonable, it cannot be harder than this. So people who try to formulate an augmented Lagrangian, people who try to differentiate here to get 2x double dot over t cubed minus 6x dot squared over whatever. No, there's no square. X dot over t to the 4. This is a second order differential equation with time varying coefficients. It's hard to solve. You can try to manipulate things together, but it's straightforward, okay? Any question? At any rate, people did, of course, very well. Quest 3, 10s. Most people got 10 out of 10. But this, no, very few got 10 out of 10. Usually get 8, 7. You have any question? No more quizzes, just one more homework on calculus operations and the topic of today that we're gonna start today. So we're gonna start a new topic, and I'll say it for the last time in this course that if you got literally nothing, you can start to benefit from something. Almost has nothing to do, particularly this lecture, almost has nothing to do. Has nothing to do with anything that you learned in this class before. We can talk about introduction to differential geometry, and geometric mechanics. Or you want to put it in one word, one phrase, differential geometric mechanics. Just to touch upon the beauty of the mathematical physics that Einstein did. We're gonna just touch upon it. But to get this flavor, we're gonna learn some useful tools towards the end, about 4 lectures. We're gonna learn some useful tools in these 4 lectures to be able to appreciate Newton's work at the end, Einstein's work. And know a little bit about relativistic mechanics, how Newtonian mechanics can be generalized to the relativistic mechanics of Einstein. So differential geometry or geometric mechanics, how geometry can come to play. So actually, a typical configuration space, you guys know what is a configuration space, right? Anybody doesn't know what is a configuration space? No shame, if you don't know what is a configuration space, you can simply ask. Any question about configuration space? So configuration space of a mechanical system is typically curved space. So mechanical systems that we keep writing their differential equations of motion, these mechanical systems are typically evolving on curved spaces or curvy spaces. Let's give an example. Example 1. Pendulum. So here is a pendulum. Here is your mass. Here is your theta. What's your configuration space of the pendulum? What's your configuration space of a pendulum? Well, it's every x and y in the plane, right? Please, if you don't understand any of this language, stop me. We're going to be very, very mathematical during these 4 lectures. Like I said, differential geometry is nightmare for mathematicians themselves. It's really very math. Okay, but we will not be experts in differential geometry. We'll just have some flavor. But if you don't understand any of the language, just stop me and ask. The configuration space simply is the set of all possible positions, right? Set of all possible configurations. This is what we know. So for a pendulum, it's every x and y in the plane R2 such that x squared plus y squared is L squared, or if the length is unity, let's take the length as unity. Okay? So simply, this is the configuration space of this guy, is this circle. This circle. In mathematics, we denote the unit circle by S1. Okay? So S1 is the unit circle. So when we write down the differential equations for the pendulum, everybody can write down the differential equation for the pendulum. We write theta double dot equals negative g over L sine theta. You can derive it immediately, right? and we write down, we say, hey, here is the point, here is the flaw. We write where, comma, theta is real. This statement is not accurate. Okay? Why? Because simply theta is not a real number. Here is the real number. Simply 0 and 2 pi, they are different points. They are not equal on the real line. But on S1, 0 and 2 pi is the exact same point. Okay? So that's fine. When we do some local analysis, we can consider theta as a real number, but globally, theta cannot be a real number. Theta does not belong to reals. Theta belongs to S1. Okay, just to be exact here. Any question about that? Any question? I mean, this causes some interesting phenomena. If you take the geometric control course, we can talk about satellites, so it leads to serious stuff, attitude control of satellites. But at any rate, even here from this picture, yeah, I mean, we understand that theta is not real exactly from an exact point of view. It doesn't belong to the real line, but belongs to S1. Any question about that? Yes, you?
Is this one any configuration?
Yeah, it is, but it's curved, right? This is the point, is that it's not flat anymore. It's curved, okay? The point that I'm trying to make here is that I'm saying the configuration space of a mechanical system, in most of the time, is typically a curvy space. I'm giving the first example, which is the pendulum. It is the second example, the spherical version of it, spherical pendulum. So, our three axes, your first rotation, your vertical plane, okay? So first rotation may be called theta, according to our usual problem that we had in the midterm and homework 1. And I also give it to the folks in the prelim. Theta, and in that vertical plane we have rotation phi. So this is our spherical pendulum. Here is the mass m. Okay? So obviously the mass m moves on what? On what surface? The mass m moves on what surface?
Z1.
What? This green length is fixed. So the mass m moves on what on what surface? I mean, it's called a spherical pendulum. It is evolving on a sphere, of course. Right? So m is moving on a sphere and just rotate like this and like that. Has two rotations on a sphere. So what is the configuration space? Well, it's every x, y, and z that belongs to R3 now, three-dimensional, such that x squared, y squared, z squared is 1 if the length is 1. And this is what we call in math or differential geometry as S2. So this is unit circle. It's one-dimensional thing. This is unit sphere. It's two-dimensional thing. It is denoted. Any point on the circle is completely characterized by one variable, theta. Tell me theta, I tell you the point. Here, every point on the sphere is characterized by two variables, theta and phi, longitude and the latitude. Give me these two numbers, I completely give you the point, right? Again, this is a curved space, okay? This is a curved space. So actually, theta changes from 0 to 2 pi, complete revolution, but phi is from negative pi over 2 to pi over 2 in this formulation. So it's not complete revolution. Any question about the sphere here being our configuration space over there was the circle, and these are curved spaces, they are not flat spaces. Any question about that? Any question? Let's get bit more interesting example. Do you need this? Anybody needs this board? Okay. Talk about double pendulum, or actually exactly the same as two-link manipulator if you like robotics. Okay, so the double pendulum, it is the thing. You have the first theta 1, this is M1, and then you have the second theta 2, M2, okay? Or if it's a manipulator, here is the base, here is the first arm, theta 1, and here is the second arm, theta 2, okay? So what is the configuration space? Let's do it geometrically. Theta 1 actually varies, it's along the circle, right? And theta 2 is also along the circle in the two cases. So theta 1 varies from 0 to 2 pi, theta 2 varies from 0 to 2 pi. So my configuration space actually is simply S1 cross S1, right? What does it look like? S1 cross S1. So I have a circle, and at each point I created a circle around it. So something like this. Here is the configuration space, is S1 cross S1, and here is S1 cross S1. It's a donut shape. So S1 varies along this inner circle, theta 1 varies along this inner circle. And at any particular value for theta 1, say this guy, we have theta 2 varies along another circle, right? It's a donut shape which we call torus. Any question about that? S1 cross S1. So again, this is a very realistic system that is evolving on a curved space. Okay? Any question? Basically, any mechanical system with a rotational degree of freedom evolves on a curved space. And, I mean, can you design a mechanical system without a rotational degree of freedom?